Hey guys, today we're going to look at how to do factoring with polynomials. And so we're going to look at a couple of the options or the methods today, and then we'll look at some other methods in the next lesson to try to get you in a position where you can factor a polynomial into smaller pieces. And so if you remember, a factor is something that you can multiply to get another number. So for example, if you're looking at the number 15, and you're talking about factors of 15. Well, 1 and 5, or 15 are factors of 15 because 1 times 15 is 15. 3 and 5 are also factors of 15 because 3 times 5 makes 15. So when we're talking about factors, we're talking about the things that you can multiply to create whatever you're trying to find. So we're going to look today at how to factor polynomials, meaning we're going to look at how we can figure out what you can multiply to get a polynomial. So it's a little more complicated than just multiplying to get a single whole number, but it's the same idea behind it. We're trying to figure out what we can multiply to get these polynomial expressions. So where we were in the last lesson learning how to multiply polynomials together to get a bigger polynomial, we're now going to look at how to do the reverse of that and break it back apart into the two separate polynomials instead. So by the end of this, you'll be able to break polynomials into factors. And we're going to use 4 methods today. We're going to look at using GCFs, common binomial factors, grouping, and a method called, or a special method called the difference of squares. All right. So let's get into this. So factors are numbers that can be multiplied to form a product. We just said that. Polynomials can be factored to break them down into smaller parts so that it makes it easier to solve problems with them. Now, like I said, there are several ways to factor them, and the way that we choose to factor depends on the structure that the original expression has, because certain structure leads us to have to use certain methods for the factoring. So this is not going to be a situation where you can pick and choose which method you're most comfortable with to factor these things. You're going to have to choose the method that will work for the type of problem that you see. So like when we did systems of equations, you could pick whether you wanted to use substitution or elimination or graphing based on what you liked best. This is not a situation like that. This is going to be, you have to look at it and say, oh, well, this is this kind of problem. Let me go and use this. That can make it a little bit tougher because you do have to learn when each method is appropriate for what type of problem. But at least it gives you a hard and fast rule for, hey, this problem needs this method. Boom, let me do that particular one. So let's get into the first method. First method we're going to look at is called greatest common factor, or GCF. You learned how to do greatest common factors with regular numbers back in probably the 4th grade. So if you maybe remember, or if you don't, maybe think back. When you have numbers like, let's say 18 and 45, and they ask you to identify the greatest common factor of 18 and 45. And so you would look at those numbers and you would be trying to figure out the biggest number that will evenly divide into both of those numbers, meaning the biggest number that would be a factor of both of those numbers. And so people who are pretty good with multiplication might very easily be able to see, oh, well, I know that 9 goes into 18, and I know that 9 goes into 45, and so that's going to be my GCF. But if that's not you, if you're not a person who looks at that and sees 9 as an option for something that goes into both, here's the strategy you want to go with. So you can take the smallest of the numbers that you're looking at, and you can list out the factors of it. So like 1 times 18 is 18. 2 times 9 is 18. 3 times 6 is 18. There's no other ways for me to multiply whole numbers and get 18. So those are all the factors. Then to figure out your GCF, you start with the biggest one, 18, and you look to see if 18 will evenly go into your other number. 18 does not evenly go into 45, so 18 is out. Then you go to 9. Well, 45 divided by 9 is 5, so 9 is good. 9 is the biggest common factor. And so you can do that. You also could make a list for the 45 as well if you wanted to, like 1 times 45, 3 times 15, 5 times 9. But sometimes that other list ends up being really long, and so if you do that, you can find the common one. 9 is on both lists. But it's easier maybe to pick the smaller number and then just start dividing with the factors of the smaller number to find the one that works for both. So that's what a GCF is. When we're looking at GCFs with these polynomials, that's what we're going to be looking for, is a situation where, I don't know why that won't erase now, but okay. We're trying to find the biggest number that will go into each of the terms of the polynomial. So you're going to break the terms of the polynomial into factors, take out the ones that are the same, the common ones, and put the leftovers inside of parentheses. Doing GCF is basically like reversing your distributive property. So let's look at an example of this down here at the bottom. So I've got this 14. I was trying to make that go away and it did the opposite. Well, I don't know what to tell about all this extra stuff that's up here, but I can't do nothing about it. So it is what it is. Okay, so down here at the bottom I have 14a, 21a squared, and 21a to the third. And so when I want to find a GCF for this, the first thing I want to focus on is the number portion only. So I'm going to focus on the 14, the 21, and the 21. So I need the biggest number that will evenly divide into those three numbers. So what's the biggest number that goes into 14 and 21 and 21? Well, I start with my smallest number that's on the list, 14. 14 does not evenly go into 21. So that's out. So then I'm going to look for something smaller than 14 that will go into 14. Well, 1 times 14 is 14. 2 times 7 is 14. So let me try 7. 14 divided by 7 is 2. 21 divided by 7 is 3. 7 works. Again, if you're good at multiplication and those facts are in your head, you probably looked at that and automatically knew it was 7, and that's great. You don't have to do this list over here with the factors if you don't need it. But it's there as a method if you decide that you need a method to be able to help you figure it out. List out your factors and find the one that works for all. So 7 works as a number, or the GCF of the number portion of this. But we also have to look at the variables and consider that there could be a GCF in the variables. So I have an A squared, and an a to the third. That means all three terms include a. So a can be included as a part of the GCF. But we have to decide how many a's would be included based on how many a's are in the three terms that are there. So this first term has 1a, this one has 2, this one has 3. We can only pick as many as are common, meaning the same, for all three terms. So if we have an a here and we have 2 a's here, and we have 3 a's here, well, the only part that's the same in all of them would be 1, because this one only has 1. The first term only has 1 available, so only 1a would be common for all three. So 1a comes out. I don't have to put an exponent of 1 on it. I can just leave it as a. And that becomes my GCF. So the GCF for this is 7a. But if we're factoring out the GCF, then we're not only identifying the GCF, but we're also going to have to put the rest of what would be the solution to, or what would be the expression once that GCF has been taken out. So this is where this starts to look like the distributive property backwards. Because I'm now going to have parentheses, and inside of those parentheses have to be what would be left over if I divided everything by 7 and a. So I like to think of this, you can think of it two ways really. You can think of it as 14 divided by 7, or you can think of it as 7 times what would give 14. So whether you want to think of it as you do in distributive property and what's missing, or you want to do division to figure that out, either way is okay. But 14 divided by 7 is 2, or 7 times 2 would make 14. Here I have an a, here I have just one a. So 7a times 2 would make 14a. I don't need an a with this term because the a is out here. So I'm going to move on to the next one. Plus, now I'm going to go to the second term. So the second term is 21a squared. I'm going to take that one and do the same thing. Either do 21 divided by 7, or think 7 times what would give me 21. And I know that that answer is 3. Now this one had a squared on it. I have an a outside, but if this was a squared, I still have that one a that's left behind on the inside. Because a times a would give a squared. So 7a times 3a gives 21a squared. So I've done that. Now I move on to the next term. Plus, well, 7 times 3 is still 21. Now let's look at our a's for this one. I still have an a outside, but I had 3 a's to begin with here. So I brought 1 a to the outside. I still have 2 a's left on the inside. So a squared on the inside. This is the factorization of that. So the 7a on its own is the GCF. But the whole thing factored with the GCF out is 7a times 2 plus 3a squared. And you can kind of double check yourself on that and make sure that you've done this correctly by doing distributive property with the term that you factored out. 7a times 2 is 14a. 7a times 3a is 21a squared. 7a times 3a squared is 21a to the third. And so we feel pretty confident that we move that in the correct way. Okay, so let's look at some examples of this. So here I have 16p to the fourth plus 4p to the third. And I want to factor out the GCF of this, or identify the GCF, factor it out. So again, we want to focus in on our numbers first to figure out the common value that will go into both 16 and 4. Again, start with your smallest and see if it'll go. If it will, then you can use that number. If not, then you got to pick factors that are smaller than your smallest number. Well, 4 will evenly divide into 16, so 4 can be our GCF here. So I have a GCF of 4 for the number. And then I got to look at the variables too. So I have p to the fourth and I have p to the third. Again, we have to pick the number of p's that would be common in both. So if this one has 4 p's, and this one has 3, well, 3 is the most that would be common in both. And so 3 p's is what we would get, p to the third. That's my GCF. But again, if I'm asked to factor it, I've got to put the leftover part as well. So 4 times 4 would make 16. So I know on the inside I'm going to have a 4 for that first term. If this was p to the fourth, and I took out p to the third, well, I still got to have another p here so that when it multiplies, it gives p to the fourth. So p to the third times p would make p to the fourth. Plus 4 times 1 would be 4. And then, and I'm trying to get this, by the way, I'm going to that second term. And then p to the third is all I have up here. So I already have all the p's I need in the term that I pulled out. I don't need any additional p's on the term I'm leaving on the inside. And so that's that. I'm finished. Again, you can double check yourself by redoing your multiplication. 4 times 4 is 16, p to the fourth. 4 times 1 is 4, p to the third. And so that all matches up the way I needed it to. All right, on to the next one. Maybe. Or not. All right, on this one, I have 28v squared, or negative 28v squared, negative 8v, and negative 36. Again, let's lock in on the numbers first. And so I'm going to look at that negative 28, that negative 8, and that negative 36. I'm looking for a number that will evenly go into all three. So I'm starting with my smallest, the 8. 8 will not go into 28, and so I know 8 is not the answer for this. 8 also doesn't go into 36. And so I need a number smaller than 8, but it's still a factor of 8. So the factors of 8 are 1 and 8, and 2 and 4. So I'm going to go to 4 next, because 4 is the next biggest. 28 divided by 4 is 7. 36 divided by 4 is 9. And so I know that 4 goes into all three numbers. So I can use a GCF of 4. Now, you might notice that all this is negative. You could also have a GCF of -4, or you could also factor out a -4. But that would not be a GCF here because G stands for greatest. And so 4 is bigger than -4, so I would use a 4 instead. But if you're ever working a problem and you needed the signs in here to change, you could factor a -4 out to make that happen. And I'll show you something kind of like that in a little bit. So I'm going to factor out a 4. Now, you'll notice, hopefully, in this one that they don't all have V's this time. I have a V squared and a V, and then I don't have a V down here with the 36. So I can't include V in the GCF this time because it's not common for all 3 terms. So I'm just going to leave my 4, and I'm going to see what I would have left over. So 4 times -7 is -28. Since I didn't move any V's, I'm still going to have V squared there. Minus 4 times 2 is 8. Again, since I didn't move any V's, I'm still going to have V there. Minus 4 times 9 is 36. I didn't have any V's anyway, so I don't have any V's there. And you can double check yourself. 4 times -7 is -28V squared. 4 times -2V is -8V. 4 times -9 is -36. And that would be the factored form of that equation. Or that expression. Okay. Let's do another one. Do a couple more together and let y'all try a couple. Okay, in this one, again, we're going to look for GCF, so we're looking at our numbers first. I have a 10, a 9, and over here I don't have a number, but it's understood to be a 1. So I have a 10, a 9, and a 1. If you ever have a number that's a 1, the only factor of 1 is 1, and so there's not going to be a GCF in this because factoring a 1 out doesn't change anything. 1 is the greatest common factor, but there's no need to factor that out. So I'm not going to worry about the 1. Let's look at the variables. I have n to the third, n squared, and n. So they do all have an n, which means I can factor an n out. Let's look at how many n's we can take. So if I factor out n, now the first one has 3 n's, the second one has 2, the last one only has 1. So the most they would have in common, meaning the most they would all 3 have, would be 1, because this one only has 1 that I can give. So we'll keep 1 n on the outside. And then I'm going to, I don't know how my pen got small there. And then I'm going to see what would be left on the inside. So since I didn't change the numbers, we're still going to have 10 for that first term. I took an n out, but I had 3 n's to start with, so I'm still going to need an n squared on the inside because n times n squared would make n to the third power. Minus 9, n times n would make n squared. And so I have n times n for the n squared. And then on the end, plus 1, and then I took an n out, but there was only 1 n to start with, so I don't need an n with that last term. That n is gone. And there is the GCF factored form of that polynomial. All right, let's do one more, and then I'll let you try a few. All right, this one we have 6n to the third minus 3n to the fifth. The number part of that, 6 and 3. I'm looking for a number that will evenly go into 6 and 3. Again, start with your smallest. Start with 3. Will 3 evenly go into 6? Yes, it will. So 3 can be our GCF. And then I got to look at the variables, the n's. I do have n's with both, which means n can be a part of our GCF here. And so I've got to decide how many we can have. That would be common. This one has 3 and this one has 5. So if I have 3 n's here and I have 5 here, the most they would have in common would be 3, because I have 1, 2, 3 in each. Now the last one has more than 3, and that's okay, but they have 3 that would be common between them, meaning they both have it. So 3n to the third is our GCF. And then when I look at what would be left over, 3 times 2 is 6. Since I had n to the third on that first term to start with, and I have n to the third already out here, I don't need any more n's for that, because 3n to the third times 2 is 6n to the third. minus 3 times 1 is 3. If I have n to the third outside, but I need n to the fifth, well, I'm going to need some more n's in here to make that. So 3 and 2 more would make 5 total. So I'm going to have n to the fifth here. And you typically wouldn't see that 1 on there. You would have 2 minus just n to the fifth. It won't let me erase that. Why is that? Who's got thoughts on that? Y'all can't answer me, but I wish y'all could. Because somebody watching this video right now already knows what in the world. But anyway, well, now that happened. Ooh. Minus n to the fifth. Okay. So that's how we do GCF. Y'all take a few minutes on the next slide and try those that say you try it. So if you'll pause the video and work on those, and then come back when you're done, and we'll see if you got correct answers or not. But please pause the video and take some time to try them yourself to make sure you know what you're doing. So it'll help you to get an idea of whether you actually understand what's going on here or not. Okay, so you're pausing it here, working these 3 out, and then coming back when you're finished. All right, take a minute and look at that and see if you were able to get those correct answers to that. If you weren't, maybe look at what I did and see if you can look back and see what went wrong. Making sure that you were looking for the biggest number that would evenly divide into all 3. And then looking for the smallest number of variables that would have been common for all 3. Okay? All right, let's move on into the next method. So the next method we look at is called common binomial factor. And this is not a super common thing to see just like on its own in a problem, but we use it in the next method that we're going to look at too. And so we want to look at it separately first. I have seen some questions like this where they give you a problem set up with a common binomial factor and you have to be able to factor that out. So it's not impossible for you to see this, but you're going to use this method to do other types of problems as well. So as we look at that, that's what you want to think about. So if an expression has what's called a common binomial factor, you're going to treat that factor like a GCF. So remember, a binomial is 2 terms. Common means they both have it. So notice down here at the bottom in this example I've given you, both terms of this, or both parts of this polynomial, this part and this part, both have a section of it with a binomial factor of 2x minus 3. That's what I'm talking about when I'm talking about a common binomial factor. So it's something being multiplied in the polynomial that's a binomial that's common for both parts, or all the parts. Typically, it's just in 2 parts. So we have a common binomial factor for this term of 2x minus 3, and a common binomial factor for this term of 2x minus 3. So if that exists in the problem that you're working on, you write it first in its own parentheses. Then you write the outer numbers in a second set of parentheses. So what I mean by that is that 2x minus 3 becomes your first factor. And then the 6 and the negative 4x become your second one. So 6 minus 4x becomes your second factor. And we're really just changing the structure of this polynomial when we do this. Because what you're looking at here is saying that 6 times 2x minus 3 minus 4 times 2x minus 3. Well, here, we could work this out if we wanted to by saying the 2x minus 3 times the 6, which is what this is showing, and the 2x minus 3 times the negative 4x, which is what this part is showing. It's just a different way to write that, a different way to structure it before the multiplication had taken place. Okay, so let's look at some examples with that. So in this first one, I have 3x plus 5 plus 7x plus 5. This x plus 5 is a common binomial factor. Both terms have it. It's a binomial. So it gets written down as your first factor. And by the way, it doesn't actually matter whether you write it first or second, but I always just write it first. And then the outside parts, those leftovers, what I like to call them, the 3 and the 7, make the second factor, 3 plus 7. So the matching piece goes first, the leftovers go second. So in this next one, 3r times x minus 4y minus 5p times x minus 4y. This x minus 4y is common. So it's going to become our first factor, x minus 4y. And then the 3r minus 5p that's on the outside will come together to make the second factor. 3r minus 5p. All right, on to this one. So this one says x plus 4 times x plus 4 times 5. But still, this x plus 4 is treated as a common binomial factor. And it gets written down first, x plus 4. And then those leftover parts create the second factor, x plus 5. All right, one more, and then I'll let y'all try a few. In this one, notice that the binomial factor in this one is 5x plus 3y, but then over here it's 3y plus 5x. You have to look at that, and even though the order is different, as long as it holds the same value, you can still count it as a common binomial factor. So 5x plus 3y and 3y plus 5x, since it's addition, the order that we add in is not going to make any difference. So this is the same as this. That counts. So we'll use 5x and 3y as our common. And then the 2 and the z are the outside parts that will make the second one. Now, had this been written with subtraction instead, 2 plus z. Like if this was 5x minus 3y and 3y minus 5x, that's not the same thing. Subtracting a 5x minus a 3y and then a 3y minus a 5x isn't the same, because when you do that, you're putting the negative or the subtraction on the 3 for the first one, but on the 5 for the second one. And that doesn't give you the same value. So when it's subtraction like that, you really got to look at it and make sure the signs are on the correct numbers for that to work out. All right, take a couple minutes. Again, pause the video, work the next slides on the next page where the you try it's are. Get the answers to those, and then unpause the video and see if you are correct. So you should be pausing the video, taking a couple of minutes to work these, and then unpausing to see if you're right. All right, take a look at these and see if, again, you got the correct answers to those. If you missed something, look back at it maybe and see if you can see the difference in what I did and what you did and the work that you put forth there. All right, let's look at the next method. So the next method we're going to look at is called factoring with grouping. This is probably the most challenging of the methods, not because it's so terribly difficult, but just because it's a lot of steps, and you need to make sure that you can get each of those steps done correctly to be able to end up with the final answer as a correct answer. So grouping is only used when there are 4 terms in the polynomial. So a very specific method to use when you got a 4-term situation. First thing we want to start with is looking for a GCF for all 4 terms first. Because if there is a GCF in the whole thing, we need to factor that one out first. So like in this example down here where I have 25v to the third, 5v squared, 30v, and 6, I would start by looking to see if there's a GCF in those 4 numbers together. And then if there is one, go ahead and take that out. If there's not, well, then I'm ready to move on and go on to the next one. So 25, 5, 30, and 6. 5 is our smallest number. 5 goes into 25 and 30, but not 6. And since 5 doesn't have any other factors other than 5 and 1, I'm not going to have a GCF in this problem. There's not a v in every term either, so I don't have a variable GCF. So I'm just going to go with it and leave it alone like it is and go on to the next step. So when there's not a GCF in the whole thing, well, then we're going to create smaller groups so we can find GCFs in the small groups. So we start by grouping the first 2 terms together and the last 2 terms together. And then factoring out the GCF in each of those groups. So again, let's look at what that actually means as we work through this problem. So if I group the first two terms, and then I group the last two terms, I'm going to look at just the first group and find the GCF just between those two terms first. So I'm looking at 25v to the third and 5v squared. I'm going to find just the GCF in that. So for 25 and 5, the number 5 will go into both of those. So 5 can be the GCF as far as the number is concerned. And then I also have v's with both. So I can use the v's in my GCF as well. So 25 and 5 both share 5. V to the third and v squared, well, my GCF for that will be v squared, because remember, we're going to pull the number that would be common for both out. If I do that, 5 times 5 is 25. V squared times v would make v to the third. Plus 5 times 1 is 5. V squared is on the outside. I don't need a v on the inside because I only have v squared anyway. So v squared times 1 would give me v squared. 5v squared times 5v would give me 25v to the third. So I factored the GCF out of the first group. Here it is. Now I'm going to go to the second group and do the same thing. So I have 30 and 6. 30 and 6 are both divisible by 6, so 6 can be the GCF for that. And then I'm not going to have a v in my GCF this time because I don't have a v with the 6. So that means that 6 is the only thing I have in the GCF. The leftovers are 5v, because 6 times 5 is 30, plus 1, because 6 times 1 is 6. Now, if you do this correctly, you should always end up in this situation where you now have a common binomial factor. The thing in parentheses should always match. If it doesn't, then you've probably done something wrong, or it may be that you can't solve that problem with grouping. So I now have a common binomial factor, which means I can use the common binomial factor method to finish this off. So I'm basically combining my GCF method, which is what I've done here. And now I'm going to use my common binomial factor method to write my final answer to this. So my final answer to this is going to be 5v plus 1, because that's the part that's common, times 5v squared plus 6, because that's the leftovers. Or that's the outside part. So just like what we were doing the other day, or not the other day, earlier in this lesson, the part that's on the inside that matches goes first, and then the part that's left over on the outside becomes the second factor. And so here is our solution to that. So that fourth step that we haven't filled in yet is write the GCFs as one factor, or one binomial factor, and the leftovers, that common binomial factor, as the other. All right, let's do some examples of this, and I have a bunch of them. So we're going to do like 6 together and let y'all try a couple. Okay, so in this one, 8r to the third minus 64r squared plus r minus 8. Start by looking for a GCF in everything. 8, 64, 1, and 8. Remember I said if there's a factor of 1 or a term that's a 1, there's not going to be a numerical GCF because 1 would be the only factor, and factoring a 1 out doesn't help anything. So we don't have to worry about a number for the GCF. We look for variables. If they all have the same variable, we would have a variable GCF. Here we don't, though, because 8 doesn't have an r with it. So there's no GCF in the whole problem, which means I need to go immediately to grouping to find GCFs in each part. So I'm going to group the first two, I'm going to group the last two, and I'm going to factor out the GCFs in each of those. So in the first group, 8 and 64, well, 8 times 8 is 64, so 8 is a factor of both. And then I have r to the third and r squared, which means I can pull out an r squared because they both have at least 2 r's. That leaves me with an r minus 8. And I know that because 8r squared times r is 8r to the third, 8r squared times 8 is 64r squared. That is the factored form of this. So now I'm going to go to the green. Again, if I do this right, I'm going to end up with an r minus 8 in the parenthesis because I have to have that piece that matches. So what can go out here that I could multiply by that would leave me with r minus 8 on the inside? Well, 1 times r minus 8 would be the same as this r minus 8 from up here. So this is the factored form of that. The only thing in common that these have is a 1. We do have to pull that 1 out so that I can create the factors that we need. And so that becomes our common binomial factor problem. And so again, when we get to here, that common binomial factor becomes our first factor. And then our leftover pieces become the second one. So our answer here is going to be r minus 8 times 8r squared plus 1. And that's our solution. And you can check yourself on that by multiplying your terms out. So like r times 8r squared, r times 1, 8 times 8r squared, negative 8 times 1. And make sure you end up with the same thing, or doing a box with this to make sure you end up with the same thing that we had here. I don't know that I really recommend that. I mean, you can, for sure. But if you want to just kind of spot check yourself instead of having to multiply the whole thing back out, you can always just maybe like check your first terms. R times 8r squared is 8r to the third. Check your last terms. Negative 8 times 1 is negative 8. And then at least we know the first two are going to be fine. And so hopefully the middle of it would have worked out the correct way as well. That kind of gives you a quick way to check and say, hey, yeah, this one will work for what I have going on here. All right, let's do another one. So I have 24p to the third, 15p squared, negative 56p, and negative 35. And I want to see if that has a GCF for the whole thing first. Now, if you are not great with looking for the GCFs, and a question like this has got so many parts and they're kind of bigger numbers this time, remember that the strategy is to go with your smallest number, think about its factors. So 15 can be 1 times 15 or 3 times 5. That's the only ways to make a 15. And then you check those factors in order from the biggest to the smallest. Well, if I'm doing that and I'm dividing these things by 15, well, 24 will not evenly divide by 15, so 15 is out. 24 also will not evenly divide by 5, so 5 is out. 24 is divisible by 3. 15 is. 56 is not. And 35 is not. So 3 doesn't work either, which means 1 is also going to be the only one that works. And factoring out a 1 doesn't matter to us, so we're not really going to worry about that. So there is no GCF for the whole problem. I just checked everything, nothing worked for the whole thing. So I'm going to go back to my grouping since there's no GCF for the whole thing. And so when I look at the first group, 24 and 15, well, those do share a factor of 3. We figured that out when we were looking at the top. So 3, and then they still have p's, they both do, so p squared. Because they're 3 and 2 is the most that they both have in common. 3 times 8 is 24. Still have a p there because I need p to the third for that first term. And p squared times p makes p to the third. Plus 3 times 5 is 15. P squared is outside, so I don't need any p's on the inside since they're both out here already. And that one is done. So now when I do the next one, I have to end up with an 8p plus 5 for this to work. Now this one's a little bit different because you'll notice that on the inside of these parentheses up here, I have minus and minus, but I've got to end up with positives in the parentheses here. So the only way to do that, to end up with the signs changing in this, is to take out a negative number as my factor. So even though that won't be the greatest, it will allow the signs to change so I can finish factoring this. So what times 8 would give us a negative 56? Or what times 5 would give us a negative 35? That's negative 7. And so when I go to give my answer to this, I'm going to have an answer of 8p plus 5. And then 3p squared minus 7. The matching piece is the first factor. The leftover pieces are the second one. So here's my match. It goes here. And here are those leftovers. And those go here. All right, let's look at another one. So on to this next one. So I have 21k to the third, negative 84k squared, 15k, and negative 60. And I'm looking for a GCF in all four to start with. So 21, 84, 15, and 60. I'm going to look at the 15 and use those numbers to figure this out. So 1 times 15 or 3 times 5. So I start with 15 because that's the biggest. 15 does not go into 21 or 84, so that's out. 5 does not go into 21, 5, 10, 15, 20. So that's out. 3 goes into 21 7 times. 3 goes into 84 28 times, I think. Let me see, 84 divided by 3. Yeah, 28 times. 3 goes into 15 5 times. 3 goes into 60 20 times. So 3 is our GCF for the whole thing. So all four terms are divisible by 3, which means 3 is a GCF for the whole problem. So I need to start this problem by dividing the whole thing by 3. Now, when I do that, I'm going to get a smaller problem to work with. I'm going to have 7k to the third minus 28k squared. Just kidding. So 84 divided by 3 is 28. 28k squared plus 5k, 15 divided by 3 is 5, minus 20. 60 divided by 3 is 20. This is the problem that I'm actually going to do grouping with now to factor it. That 3 that I took out from the beginning is gone as far as I'm concerned, except that when I give my final answer, the whole thing has to get multiplied by 3 because I divided the 3 out to start with. I got to multiply it back in at the end. So I'm going to put a 3 on the outside here to represent that 3 that I took out, and then I'm going to put my 2 factors that I end up getting into the space here and here. So I'm going to have it here and here with my 2 factors. So I got to look at this and do some grouping with this. So I'm going to group those first 2 terms, group my last 2 terms, and then figure out our GCFs in those. So for 7k to the third and 28k squared, 7 will go into 28. So 7 would be our greatest common factor there. And since I have k's with both, I can do k squared as part of the GCF as well. And so that leaves me with 1k, because 7 times 1 is 7, and k squared times k would be k to the third, minus 7 times 4 is 28. And I don't need any k's with that because all the k's I need for that term are on the outside. I only need 2, and they're both right here. So I go to the next one. I need to end up with k minus 4. And so what would have to come out of this to turn it into a k minus 4 would be a 5. Because 5 times k is 5k, and 5 times 4 is 20. So I'm going to have a 5 on the outside here. It's a positive 5 this time, because I didn't need the signs to change. And so our answer to this ends up being the k minus 4 as one factor, and 7k squared plus 5 as the other. And then, of course, that 3 that I talked about has to be a part of our answer, because we divided it out at the beginning, we got to multiply it back in at the end to make it stay equivalent. So this is our solution to that one. All right, let's see if we can get another one real quick. So here I have 105, 175, 75, and 125, and I want to look for a GCF in this as well. And since they all end in 5, I know I'll have one because at least 5 would work. Now, you may want to check for some numbers bigger than 5, because if there's a bigger one, you want to pick the biggest that you can. So if 5 works, then you might try things like 15 or 25 and see if any of those work. If you do, though, and you start doing some division with that to check it, like 105 divided by 15, well, that's 7, so it works for that. But 105 divided by 25 is not a whole number, so we can't use that. So 15 maybe, but if I do 175 divided by 15, I get 11.6 and some craziness. So 15 is not going to work either. 5 is the GCF for this. So we're going to pull a 5. We don't have to put an n or anything with it because there's no n's in all 4 terms, just in 3 of the 4. So n's not going to be a part of it. So 5 gets factored out from the start and becomes a part of our final answer at the end. But we're not going to use it when we're factoring this problem, using the grouping method. So 105 divided by 5 is 21. 175 divided by 5 is 35. 75 divided by 5, 15. 125 divided by 5 is 25. And I noticed that I made this a 2 and not a 3 up here, so let me fix that. See if it might not let me, because of course it won't, because it's strange. I don't get it. Okay, well, I'm just going to turn it into a 3. Let's go with it like that. So this is the problem I'm actually going to do grouping on at this point. So I'll group the first two, then I'll group the last two, and then I'm going to work off of that. So 21 n to the third and 35 n squared. 21 and 35 are both divisible by 7. And then I'll have an n squared as well because they both have n's with them. So that'll leave me with 3n plus 5. 7 times 3 is 21. 7 times 5 is 35. So in the second group, I have to end up with 3n plus 5 in my parentheses. So to make that happen, I'm going to have a sign change again, which means I've got to factor out a negative number. Negative 5 times 3 would be negative 15. Negative 5 times 5 would be negative 25. So a negative 5 would work for that. So in my answer to this, I'm going to end up with 3n plus 5 and 7n squared minus 5 as our factors. And then, of course, the 5 that we factored out from the start becomes a part of our solution at the end. I should have done that in blue, but I didn't. So, oh well. All right. Maybe look at a couple more, and then we'll let y'all try a couple of these. So here I have 24r to the third minus 64r squared minus 21r plus 56. Again, looking to see if there's a GCF in all of it before we start. So factors of 21 are 1 and 21 or 3 and 7. 21 will not go into 24 evenly, so I'm going to skip that. 7 also does not, so I can skip that. 3 will go into this and this, but not into 64 or 56. And so there's not a GCF for this one, which means we'll go straight to our groups. We don't have to factor something out at the beginning. So in the first group now, let's look for a GCF in just that group. 24 and 64 will share a GCF of 8. 24 divided by 8 is 3. 64 divided by 8 is 8, so that works. And they also share an r squared because they both have r's. Leaves us with 3r minus 8. And then in the second group, I got to figure out the same thing. I've got to end up with 3r minus 8. So I got to have a sign change again. I'm going to pull a negative 7. Negative 7 times 3 is negative 21. Negative 7 times negative 8 is positive 56. And so the factors for this end up being 3r minus 8 and 8r squared minus 7. Okay, so let's just do one more together and then let y'all try a couple of those. So looking at this next one, if I do grouping with this the way, first of all, look for a GCF. 4, 6, 1, and 24 are not going to have anything in common other than 1. And so I don't need to factor a GCF out of this, which means I can go straight to grouping. But if I do grouping with this one, notice what happens. 4 and 6 have a common factor of 2. That leaves me with 2xy plus 3. In that second set over there, I don't have anything in common. So all I could factor out is a 1. That would leave me with negative x minus 24y. And that doesn't match. So this doesn't work for me to do grouping the way that this is written. So I'm going to have to back up and do something different. Just because it doesn't work to do grouping the way it's written now doesn't mean it's not possible to factor it. We might want to look to see if maybe we could rearrange it into something that you could factor. And so when you look at this and you look at these terms and have a 4xy and a 6 and a negative x and a negative 24, I have some things here that maybe would go together better if they were in a different order. Like 6 and 24 share common factors. I know that. This x would share a common x with this term up here. And so if I can rearrange these two, maybe I'll have something that I can work with a little bit better. So we're going to try that and see what happens. I'm just going to swap places with those. So I'm really going to try this as 4xy minus x in one group, and then 6 minus 24y in the other. And now we'll factor with those two groups instead. And that would be a positive 6, by the way. So let me put that plus back down right here. So looking at that first group now, 4xy minus x, I can pull an x out of that and leave me with 4y minus 1. And in my group with the 6 minus 24y, well, I can pull a 6 out of that and leave me with 1 minus 4y. Now, this is closer, but I'm still not quite where I need to be. I have a positive 4y and a negative 1. I have a positive 1 and a negative 4y over here. So remember to get your signs to change so that they'll be the same signs in both. All we have to do is change that 6 to a negative 6, and that'll change all my signs so that they now match up. And so the factorization of this would be 4y minus 1 and x minus 6. So it is possible to rearrange them if you need to. I don't actually think you're going to see something like that on the state test, but you could see that on the ACT where you have to rearrange something to be able to factor it correctly. So you kind of want to watch for things like that as you're doing these. Okay, take a couple of minutes and work through the examples on the You Try Some slide on the next page. And then when you get done, come back to this video and see if you were correct or not. Please take some time to pause the video and try these yourself. Because if you don't, you may find yourself unable to do them on your own when you get to the practice on it. So take a minute, pause the video, and see what you can do. Okay, hopefully you took some time to work through these. So here is mine worked out, or here are mine worked out, and I want to let you look up close at them real quick, especially this first one. So look at your answer to the first one and then look at mine and see if you got the same thing. Notice that we had to factor out a GCF of 3 across the whole thing to start with, because a 3 would divide evenly into all 4 of those terms. That 3 came down to be at the beginning of my final answer. And then I factored in grouping what was left over. And so when I did that, I had these two groups, factored those into this, and then those factors turned into 7n plus 6 and 3n squared minus 5. If you missed that, maybe pause it and look back at it and make sure that you can understand kind of where that stuff came from. And then in the second one, kind of the same thing, although I did not have a GCF to worry about in the second one. So in this one, I ended up grouping the first two, grouping the last two, and then just factoring out from each group what we needed to. That gave me a 4p minus 7 as our common factor, and then our leftover parts here to give the second part of that. Okay, so that's factoring with grouping. And then the only other method I want to show you today is a special method that's used on binomials with a certain structure. So this is called the difference of two squares. And so we can use this special method if you have a special kind of binomial that's a subtraction binomial. Let me use a different color here, wait. Remember, binomials are made of two terms. So made up of two terms that are both perfect squares. So remember, a perfect square is a number whose square root is a whole number. So like 1 times 1 is 1, so that makes 1 a perfect square because its square root is 1. 2 times 2 is 4, that makes 4 a perfect square because its square root is 2. 3 times 3 is 9, that makes 9 a perfect square because its square root is 3. So on. So if you recognize a subtraction binomial as being a difference of squares problem, you can factor it using this formula. The formula says that if a squared minus b squared is your problem, then that's the same thing as a plus b times a minus b, where a and b are both roots. So So you can recognize your terms as perfect squares if, number one, they have an even exponent. So if you have an exponent term and it's even, an even exponent is a perfect square. Or if your coefficient is a number that has a whole number square root. Now, if you don't know perfect squares off the top of your head, just check them in your calculator. Do the square root of the number and see if the number you get is a whole number. So for this example down here, a to the fourth is perfect because it has an even exponent. 9 is perfect because the square root of 9 is 3. So to factor this, I take the square root of both terms. The square root of a to the fourth is a squared. You just half the exponent on it to be able to get its square root when it's an exponent term, because a squared times a squared would be a to the fourth. 9 square root is 3. Those are the numbers that go in. Sorry, I hit the pause button by accident. Those are numbers that will go into our factorization. And so we end up with a squared plus 3 and a squared minus 3. That's the factorization of that problem. And so these are very easy to do, especially if you know your square roots pretty well. If you don't, again, you just check them in your calculator and be okay. So let's look at some. So here I have 16n squared minus 9. 16 is a perfect square. Its root is 4. So the root of 16n squared is 4n. 9 is a perfect square. Its root is 3. And so I can quick factor this into 4n plus 3 times 4n minus 3. That's our factors. All right, with this next one. So I'm checking 4. The square root of 4 is 2. So 4m squared is a perfect square. Check 25. The square root of 25 is 5. So 5 is a perfect square. Subtraction again, so this one fits that category. So our factors are 2m plus 5 and 2m minus 5. All right, a couple more. Same deal here. Let's check these. So square root of 1 is 1. Square root of r squared, it's even, so it's going to be just r. Both of those were perfect, so we can do that as 1 plus r and 1 minus r. All right, and then the last one. N to the fourth has an even exponent, so it's perfect. 100 square root is 10, so it's perfect. So we can use that method on this as well. Remember, if your exponent is even, all you got to do to figure out its root is to half it. So half of n to the fourth is n squared. And so we get n squared plus 10 times n squared minus 10. All right, y'all take a minute, go to the next slide, try those, pause the video, and then come back and see if you were right. Again, you should have paused the video to try these problems out. If you've not done that, pause it now, try them, and then come back. Okay, so check yours against what I got here and see if you were able to get those same correct answers of 7x plus 10 and minus 10, n plus 5 and n minus 5, and 3x plus 1, 3x minus 1. Okay? All right, so let's look at how this might be tested. So here is a test prep question. It says, which expression is equivalent to 4a squared minus 9b squared? So hopefully when you see this question, you notice that this is subtraction, and 4 and 9 are both perfect squares, which means this is one of those difference of squares binomials that you could factor using the difference of squares formula of the root of this plus the root of that, the root of this minus the root of that. And so this will work out beautifully to do that. Remember, the root of 4a squared is 2a. The root of 9b squared is 3b, because we're just doing square roots there, y'all. And so we're looking for one that shows 2a plus 3b and 2a minus 3b. And that would be answer choice C down here. Okay. Let's look at another one. 18 asks us to find, or this question, this is slide number 18, asks us to find the greatest common factor of these terms. So remember, when you're looking for greatest common factor, you're looking at the number first. What is the biggest number that evenly divides into both of those numbers? And the good thing about multiple choice questions on this is if you're not sure, you can test out the numbers that you see down there and see which one is the biggest that will go. So if you want to test out 8, 8 will divide into 8 evenly, but it will not divide into 12 evenly. So we know that the ones with the 8 in them can't work. 4 will go into 8 and 12, so 4 is good. And then we got to look at the exponent part. Remember, for the exponents, you're looking for the most that they both have in common. So it has to be a number that both of them have, but the biggest number that they both would have in common. So when I'm looking at the x's here, I have a 4 and a 3. The most they both have is that 3. So they both have at least 3. One has 4, but it has at least 3. And so we would pick B for that. All right. Moving on. This one wants to know which of these tables is completed correctly. I personally look at this and typically just go and see if I can find mistakes in the table. So like if I'm looking at the first line and I see that they have the expression, they have the factored form of it, you could approach this one of two ways. You could either go and factor this to see whether you get this one or this one or this one or this one. Or you could always go to your answer choice and multiply it back out to see if it gives you the original problem, right? So either way would work. If you're going to factor it, which is what we've been practicing, so that's what we'll do for this. If you're going to factor it, then you got to remember that 9x squared and 6x are not perfect squares. 6 is not. And so we can't use the difference of squares deal on this one. But we can factor out a GCF. 9 and 6 both share a common factor of 3. And they both have an x, which means x would be part of the GCF as well. So this one and this one both only factor out a 3. They don't factor out the x with it. So those are not going to be correct answers. But this one that has a 3x or this one that has a 3x, well, those both could be fine. So we're now down to 2. We 50-50'd at this point. And so let's look at the second expression, see if we can figure out whether it's right or wrong. And so we have 4x squared minus 1, and we have one that says it's 2x minus 1 times 2x minus 1, one that says it's 2x minus 1 times 2x plus 1. So this one is also subtraction. It's a binomial, and 4 and 1 are both perfect squares, which means I can use the shortcut on this. I can do the roots of both of them and do them with plus or minus, which means D has to be the right answer for this, because it's the only one that shows it with the plus and the minus. All right, 20. This one wants to know which of these binomials is a factor of that problem, which means we need to factor that problem to figure it out. This problem has 4 terms, which means to factor it, we have to use grouping. So I'm going to group the first 2, group the last 2, and then find GCFs for each one. So looking at the group I have in red, 3 and 3 share a common factor of 3, because 3 will divide into both of those, and they share some x's. We have 3 x's in the first one, 2 in the second one, which means they have 2 x's in common. 3 times 1x would make 3x to the third, plus 3 times just 1 would make 3x squared. I said 3. I meant 3x squared times x would make 3x to the third, and 3x squared times 1 would make 3x squared. Sorry, y'all. And then in the blue group, we got to do the same thing. We need to end up with x plus 1 in the parenthesis, because I know if I'm doing grouping right, that will happen. So what can I multiply by x plus 1 so that I end up with an x plus 1 like I had to start with? Well, the only thing that we could put there would be a 1, because that's the only thing that won't change it. And so when I look at that, my factors will be x plus 1 and 3x squared plus 1. So out of my answer choices here, the only one that shows up from that list, that's one of the binomials I just got, is A. All right, and then we have this one. So this one wants to know which of these is true. Notice that we have a squared minus b squared, and we have a squared plus b squared. There is no formula for the sum of two squares. So something like this doesn't have a formula like this. The formula is for the difference of squares. So these are both out because of that. Now this we have difference of squares, and we have an option of a plus b, a minus b, and we have an option of a minus b, a minus b. It is plus and minus that we have to have there. So A is the right answer to that one. And then our last one asked us to find the GCF for 30x squared and 45x to the fifth. And again, we're given some answer choices, so you can check to see if 5 or 15 will fit into 30 and 45. And so 30 and 45 are both divisible by 15, which means 15 is going to be the greatest common factor because it's bigger than 5. And so then we have to look at our x's to decide how many of those would go. I have x squared and x to the fifth. You have to have the number that is common in both. So if you have an x squared and an x to the fifth, the most they both could have is the x squared, which would be this one. So 15x squared is the GCF for that. Okay, we're going to stop right there. If you'll submit those to your notes on factoring polynomials part 1, and then you are ready to practice. Y'all have a great day.